Have you all joined the Google Classroom? If not, do immediately. Again, I will post the link in the chat box. Okay. Totally 146 students are joined. Please join immediately. Those who are not joined in the Google Classroom. I have posted the link in the chat box. Please make use of it and please join immediately. Mom, strength is 180, no, mom?
Yes, ma'am, 181. I'm asking them to join, ma'am. They'll now only 170. Yes, ma'am.
146 only joined. Please, students, join. I have posted the link in the chat box. 149 joined. 3 students now joined. No, is like that. Please, if not, do immediately. I share my screen. Is yesterday class what we have discussed? Discussed about formal proof, right? What is the proof and why we are using the proof? Yes. Then formal proof and what are the notations we may use for that proof. And we have two types of statements. One is if H, then C, and another one is if and only if. Okay, if H, then if and only if C. So these are the proofs. These are the basic proofs. So with the help of this, we can prove any theorem or we can prove any concept. Okay. We have seen this theorem yesterday. Is here only have stopped, right? This is the theorem which saying that let x be a real number, ceiling of x equal to flooring of x if and only if the particular x is an integer. Okay, is it so? This is this concept, I mean this fact already we know. We have to prove here. Okay, for that we are here. This is the example for if and only if theorem. So we have if and only if means we have two parts. One is if part and another one is only if part. Okay, this slide already we have seen yesterday. Now we are going to the proof, how we can prove that. Okay, just I am assuming that first of all I assuming that floor of x equal to ceil of x. Okay, I just assume that both the things are equal. Okay, and make the particular concept or particular term as the zeroth equation. Okay, zeroth term. Okay, then I'm going to prove that particular x is an integer. Okay, using the definition of floor and ceiling, we know the definition of floor and ceil, right? What is by floor? What is my floor function? Students, What is meant by floor function? Yes, Leela, Nitya, please.
Ma'am, it gives the greatest integer which is less than the
Floor is the
greatest integer less than the value.
yes.
Than or
It
equal
is
to.
a greater integer that is less than or equal to the particular value. Okay, for example, if you have 3.5 means the floor value is 3 and seal value is 4. Okay, the particular value x equal to 3.5 means the floor value is 3 and seal value is 4. Okay, so this is the floor and seal function. Using this definition, I can say floor of x is less than or equal to the particular x. Okay, with the definition, I can say this is the we know already in maths we have studied what is the floor function. So from that, I can say floor of x is less than or equal to particular x. And next one, seal of x is greater than or equal to particular x. Okay, this is the two definition. This is the two terms I have taken from the definition of the floor and seal function. Already we have in maths. Okay, so I consider this is the first equation and second equation. Okay, but we know floor of x and seal of x are equal. How we know? Already we have assumed that floor of x and seal of x are both are equal. Okay, and now I'm going to do what? Substituting the zeroth equation in the first equation. What is the zeroth equation? Floor of x equal to seal of x. This is the zeroth equation. Now I'm going to substitute this equation in the first equation. Okay, first equation is nothing but what? Floor of x is less than or equal to x. I'm just replace the floor of x with the seal of x because both are equal, right? Floor of x is equal to seal of x. So just I'm doing what? Okay, I'm substituting zeroth equation, the first equation. The first equation is nothing but floor of x is less than or equal to x. Here in the zeroth equation, I have assumed that floor of x equal to seal of x. So I just replace this floor of x with a seal of x. Okay, so I'm getting that equation as seal of x is less than or equal to x. This is the third equation. Okay, so now from third and first equation, okay, from this third equation and the first equation, I can conclude that here the first equation is nothing but floor of x is less than or equal to x and seal of x is the less than or equal to x. Both are same, right? But in the name of floor and the seal is the different. So I can conclude that particular seal of x is the x. Okay, so x means we know already what is by x. We are just want to prove that x is an integer. From this two equation, I can conclude that the seal of x is nothing but particular x. Then only I can say this statement is true. So if we conclude, if combine these two and compare these two equation, 1 minute. Okay, fine. So from these two equation, I can conclude that particular CL of x is nothing but x. Okay. When we can get the CL of x is x, particular number is a whole number, then only we can get, right. Otherwise, if it is not a whole, I mean, if it is the particular number is not an integer, definitely we are not getting the CL of x equal to x. If not an integer means definitely we get the CL of x is greater than the x only. Okay, so we can conclude that particular CL of x is x. Okay, from the, like that we can prove that particular floor of x is also x with the same terms. Okay, if we are replacing this CL of x with the floor of x means, then I can conclude that this equation both are same only. So I just want to explain this only. With the help of we are assuming that both the terms are equal, so I can just replace one by another. So I get the conclusion is CL of x is x and floor of x is also x. Okay, thus x is an integer only if part assume x is an integer. By definition, when x is an integer, both floor and ceiling are equal to x. Okay, with the definition we know, we can say that if both the things are equal means that definitely the x will be the integer. Okay, no other floating or any other numbers. Okay, this is the way we can prove that particular theorem. Okay, this is an important theorem, please make a note of it. Is very important. Okay, very important. Let x be the real number means, and floor of x and CL of x are the same if and only if particular x is an integer. Okay, so next topic, I'm moving to the next topic, that is the additional forms of proof. What are the ways we have to prove the particular statement or particular concept? Okay, what are the techniques, what are the methods we have to prove some concept? Okay, we have some technique that are about sets. With the help of the sets means we know, right? In the maths you have studied sets with the help of union and intersection, like that. Based on that we can prove the particular statement. Otherwise we can go with the contradiction. Contradiction means what is that? The name itself you can say, right? Contradiction. If you're taking the contract answer, I mean opposite to the particular statement, and try to prove the particular opposite statement is false means the definition, the given statement is the true, right? This is the proofs by contradiction. We will see one by one. Next one is the counter examples. Okay, these are the three ways we can prove the theorem. So how we can prove with the help of sets? Here having that a statement as R union S. R is one set and S is another one set. R union S equal to S union R. Is it correct or not? Is it correct only? No, both the things are, we have two separate sets, just combining both the things. And if you can say with R and S or S and R, okay, both the things are same. If you're you can say that if you're saying that R union S equal to E means, and you're just assuming that S union R is the F, then with the help of cumulative law, we know, right, what is by cumulative law? This is the cumulative law definition. Okay, from that we can say both the things are equal. Okay, an element X is in E is nothing but this one. Okay, in E if and only if X in the F. Okay, and like that the likewise we have the another term also, X in E, then X is in the F also, because both the things are having the combination of R and S only. So the element X, if it is present in the R union S, definitely it will be in the S union R also. Okay, How we can prove this? How we can prove this? Just think how we can prove. Okay. In order to prove two sets are equal, we have to prove that if X is the member of, X is nothing but one of the element in the set S. Okay. X is the member of S, then X is also a member of T. Okay. Otherwise, X is the member of T, then X is also the member of S. Both the things. I mean, what is the meaning? Particular S is a particular X is the number, X is the element which is present in S. The particular S is the subset of T. Okay. And otherwise, X is present in T and T is the subset of S. Both the things are acceptable, and we can say particular both union of both the things are same with the help of this. Okay. If the X is available in S and available in T means, then we can say R union S is equal to S union R. Okay. We have one theorem. We know already in we have studied in maths and discrete mathematics subject also. R union S intersection T is nothing but we can state in this way also, right? R union S intersection R union T. Okay, both the things are equal, but we have to prove. Okay, how we can prove? We have to show that if X is nothing but one of the element in the particular set. Okay, here I'm taking this whole left hand side, the X in the left hand side, then X in here also. Okay, if I showed that the particular element X present here and so here also present mean, then I can say both the things are equal. Okay, otherwise if I'm taking this right hand side and take one element and again the same thing, if I show the same thing in present in the left hand side also, then I can say both the things are equal. Okay, both the terms are both the left hand side and right hand sides are equal. Okay, here I have this is also one of the example of if and only if. This is the proof of if part, first part. Okay, just I'm taking that particular element X. This is the first one, right? I'm going to prove this. The element particular X is present in the left hand side. Okay, then I have to prove that the particular element X it's also present in the right hand side, so that I can prove both the things are equal. Okay, proof of if part. This is the statement and justification. Okay, so first statement I have taken as the given problem. X is in R union S intersection T. That means I have taken as particular element X is present in the left hand side. Okay, so it is the given one. And next one, X is in R. I mean from this the statement first one, from the first statement and definition of union. Okay, from the first statement and definition of union, I can say X in R. Okay, see here X in R. Here it meaning that X in I'm just first in first step I have taken as the particular element X in present in the left hand side. What are the elements? What are the set we having in left hand side means R union S intersection T. Okay, so I can say the particular X is present in the set R. Otherwise, X in S intersection T. Is it so? With the help of this first point and the definition of union, I can say the particular X is present in this term or this term. Okay, particular X is present in R, otherwise here. Okay, both the things are union, right? So whether the particular X may be in R, otherwise this term. So the third one I have taken as from the second equation, from the second point and definition of intersection. Okay, what is the definition of intersection? If the element is present in both the sets, then only I can define in the intersection set, right? So based on the second point and the definition of intersection, I can say that X is in or X in both the things. It is an intersection, right? So what are the elements are present in both the sets? Then only I can mention the particular elements in the intersection. So I can say the particular X in R, other R, I mean R means X in the set R, otherwise X in both S and T. Okay, is it so? So from the definition 2 and the from the term from the point 2 and the definition of intersection, I can say this statement. Okay, you please read each and every term and you can able to understand. This is the third point. Just I'm taking the element in the left hand side. I'm trying to prove that particular element is present, also present in the right hand side. Okay, this is the this is my problem. I'm going to do this only. So I just stated 3 points. Now my fourth point is from the third and definition of union. My third point is nothing but X in R, the particular set R, otherwise X in both S and T. Okay, so I can say X in R union S, R union T. Is it so? Can you able to follow? The particular element is present in the whole set R, okay, capital R. Otherwise, particular X is present in both S and T. Both the things. Both, if the particular element is present in both the sets, then only I can mention in the intersection. So I can say X in R union S or R union T. Okay, this is the intersection. So I just combine this RS and RT. Okay, both the things are from the point 3 and definition of union. This is also from point 3 and definition of union. Okay. Okay, the 5 points are discussed. Now I can conclude that from the point of 4, 5 and definition of intersection, I can say here I have stated that X in R union S, and here I have stated that X in R union T. So I can say X in R union S intersection R union T. Okay. So my right hand side is proved. So here proved that a particular element X in right hand side. Okay, I have taken with that left hand side and with the definition and the points given. With the help of this, I can prove that the particular element is also present in the right hand side. So the theorem is proved. Okay. The next one, here I am taking the right hand side, particular element X is present in the right hand side. Okay. And trying to prove that a particular element X is also present in the left hand side. Okay. Please go through the go through this part, and can you please anyone try to explain? The same like previous one. Here I'm taking the particular element X is present in the right hand side. Okay, and want to prove that particular element X is also present in the left hand side, opposite to the previous one. Can you please anyone go through and explain this? Okay, students, anyone can able to follow this? Give me a response.
Yes, ma'am.
Okay, can you justify this, Pragnashya?
Um, okay, ma'am. So, 1 minute, ma'am.
Okay, fine. What about others?
Ma'am, can I say, ma'am?
Yes, ma'am.
So, if X is in R union is intersection R union T, we can say that it is X is in R union X. S.
Okay.
With the help of definition of intersection, and
Okay.
we can also say that it is also present in R union T.
Okay.
So, if X is in R, it is also both in S and T. Like we can tell it with the help of unions because it is present in both with the
Yes.
help of 2 and 3. Yes, ma'am. And after that, if X is in R, um, this thing. Okay. With the help of the fourth definition, we can say the fifth one, like if X is in R, S intersection T. Mom, didn't get the fifth one. Could you please tell me that?
What, ma?
Can I tell?
Yes, yes.
Okay.
Ma'am, if X is an R union S intersection R union T, then it should be in both R union S and R union T, ma'am. And if it is in both 2 and 3, then X is either in R or in S, both S and T, or in both.
Okay. Okay.
So X should be in R, or it should, if it is in both R, S and T, so it will be in S intersection T also.
Okay.
So X is in R union S intersection T.
Here in the fifth point, that states that X in R, otherwise X in S intersection D, R. So I can say the particular point like this. Okay, with the help of union definition. So the now I got the left hand side. So just the particular element X is present in the both the left hand side and right hand side. Okay, so the theorem is proved. Yes, thank you, Pragnashya and Leela. Yes, next theorem is nothing but contrapositive. I can say it is a contrapositive. Okay, it is one of the method to prove. Okay, this is nothing but this is the one of the method to prove the theorem or term, some concept, anything like that. Okay, we are using this proof. You can say this is one of the method to prove the theorem. Okay, contrapositive is nothing but to prove F, H, then C. Okay, if you are going to prove this statement means I can take like if not C, then not H. Okay, contrapositive, opposite. I am taking in opposite manner. Okay, if H, then C. I'm going to prove my problem is nothing but if H, then C. Okay, but I'm not going to prove the statement directly. I'm going to take the particular statement in opposite way and trying to prove the particular one is true. Okay, if H then C means I can prove that if not C then not H. Okay, both are equal, right? Just taking in opposite direction. Okay, for example, here we have one example. If it is my car, then it is red. Okay, if it is my car, then it is red. This is equivalent to if H then C. Okay, for this statement is equivalent to if H then C is equivalent to how can I say this statement in contrapositive manner means if that car is not red, then it is not mine. Okay, is it clear what is by contrapositive? We are taking the particular term or a particular statement in opposite way. Okay, to prove if H then C means we would prove that if not C then not H. Okay, you remember this example, then it will be easy for you. If it is my car, then it is red. Okay, how can I say this statement in contrapositive means if that car is not red, then it is not mine. Okay, is it clear? This is the way we are going to prove. This is the contrapositive method. The same thing also here with some other example. Okay, and here I have one example. An integer x is called even. Okay, we know what is my odd, what is my even, right? An integer x is called even or odd, anything it may I can say here, I can take the even. An integer x is called even if there is another integer x for which is x equal to 2k. Two integers are said to be have the same parity if they are both odd or both even. Okay, for mean that what is the meaning that we are going to prove this if the integer x is called even. Okay, for that I'm doing that even means I'm taking the x is even. For that I'm going to calculate the value 2k. For example, if it is the even value, I mean even integer, the k is even means what is the answer? What is the answer? The x is also even, right? If I'm giving the value, I mean integer is even number means my output also even. If I'm giving the odd value, okay, if I'm giving the odd value, 3 is the odd number, right? What is the answer? The same thing, even. Okay, if you want to go for odd means you need to go with what? 2k plus 1. Okay, so this is one of the example. We will how we can solve this. See here, this is the example for contrapositive theorem. Okay, this is the example for contrapositive theorem. If the integer is x means is called even, then the x equal to 2k. If you are taking the odd value means you have to go with what? X equal to 2k plus 1. Okay, this is the theorem we want to prove. How we can take, we'll see how we can take in the contrapositive manner. If x and y are two integers for which x, y is even. Here we are doing with addition, no issues. In the previous case, we have just multiplied. Then x and y have the same parity, right? Is it so? If we are having two numbers, x and y, okay, when we are getting when we are getting the even number in terms of addition, I'm taking the x value as 2 and y value as 3. Then what is the output? That is 5, right? This is odd or even? Odd number, no? And if I'm taking the value as both the values are even, 2 plus 2 means definitely I will get the even value. Okay, and if I'm adding two integers, that is both are odd, 3 plus 3, and so I'm getting the answer is even. Okay, so what is the meaning that if x and y are two integers for which x, y is even, then x and y have the same parity. Both the parity is nothing but even or odd. Both the integers having the same parity, then I can say particular addition also the even. Okay, how can I take this in a contrapositive manner? I can take if x and y are two integers with opposite parity, then the sum must be odd. Is it possible? Both the things are equal, right? Both the things are equal. X and y are two integers for which x plus y is even. We are taking two integers. I'm going to add the particular two integers. Both the things are even. Then both the integers are the same parity. Okay, same parities. Both the integers are odd or both the integers are even. Then definitely I will get the answer as even. Okay. And how can I take in the contrapositive manner? If x and y are two integers with opposite parity, their sum must be odd. If I prove this, this statement also true, because I'm taking in the opposite manner two integers. Yes, I'm taking the two integers with the same parity here. Okay, with the same parity, but I'm taking here is the opposite parity. Okay, here the addition is even, here the addition is odd. So it's a way of represent the particular statement in contrapositive manner. Okay, assume how we can prove. Assume x and y have opposite parity. Okay, please you assume x and y have the opposite parity, or opposite parity means one is even number, another one is odd number. I can say 2 and 3. Okay, x and y are 2 and 3. Since one of these integers even and the other hand there is no need to mention x is even and y is odd. Any one is odd, any one is even. Okay, from these two. And thus there are integer k and m. Okay, just I am taking for doing the addition, proving this particular theorem. K and m, for which k is nothing but, what is that? X is nothing but particular value, right? X equal to 2k. Okay, and y equal to 2m plus 1. How why I am representing like this means, this is the we have two terms, right? X and y. I have to go with opposite parity. That means one is even, one is odd. So that I'm mentioning with this is even, for the even value just mentioning, and this is for odd value. Okay, I can't say the first one is even, second one is no issues. If you're taking two values, any two values you substitute with this, you will get the even number of x. Okay, even the particular x is even. If you substitute one value to this formula, definitely you will get the odd number. Okay, just for the purpose I'm doing this. Okay, x equal to 2k. That means the even number. 2m plus 1 is nothing but odd number. Definitely if you are passing any number, it will give the even and odd numbers. Okay, then we compute the sum for x plus y. We are going to do that one, right? X plus y. So 2k is nothing but even, first term x, and I'm going to add with 2m plus 1 another one term. This is y. So how can I do the addition? Yes, I have taken the 2 outside. Both the things are having the 2. So I have taken 2 outside and k plus m plus 1, which is an odd integer by definition. If you want to substitute anything, please substitute here. Definitely we will get the odd number. For example, 1, k is 1, m is 1. What is the answer? 2 to 4, 4 plus 1, 5. Okay, this is odd. And I'm going to do what? 2 means what? 4. And then 2, 4, 8 plus 1, that is 9. If I'm taking with another one is 2, another one is 3. One odd number, one even number. So 5 into 2, 10 plus 1, 11. So if we're given execute with any numbers, it definitely will give the odd value. Okay, definitely it will give the odd value. Okay, so my proof, my statement, I mean, if I'm taking the contrapositive theorem, right? So this statement is true for me. I'm taking two integers x and y, adding both the things, definite with the opposite parity. That's why I mentioned with the 2k 2m plus 1. Okay, opposite parity. When I'm adding this, definitely I will get the odd number. It means that this statement also true. What is this statement? X and y are two integers. We're going to add this. If it is the same parity, definitely will be a even number. Okay, is it clear? This is the example for contrapositive theorem. Okay, like taking the statement in opposite way and try to prove that. If it is proved, then I can say the given statement also proved. Okay, can you able to follow, all of you? Can you able to follow? Anyone, please?
Yes, ma'am.
Okay. Thank you, Nityashree. Only Nityashree and Leela, Pragnashya only answer. What about others? What about boys? Anyone from boys? Can you respond? Can you able to follow? Ongoy responded in last week. Jacob, are you there?
Yes, ma'am.
Can you able to follow, Pa?
Yes,
Are you
ma'am.
following? Okay, good. 170 members are there, but 3 more people's only responding. Okay, if I will expect more than 10 responses. Okay, if you are responding in more than 10 people responding, then I will be happy, and I don't want to point any one of you. Okay, if not means some other case I want to point anyone and ask you a question. Okay, please interact with me. Try to give answer, whether it is right or wrong, no issues. Please try to interact with me. And the next one is the proof by contradiction. Okay, contradiction is nothing but we can say if H then if H then C means how to prove that H is true and not C. C is the false, implies falsehood. Okay, taking the can you able to differentiate contrapositive and contradiction? The contrapositive, if H then C is transferred to if not H not C. Okay, here taking the H as it is. Okay, if H and not C only, so the actual the state in the case of contrapositive we are stating that contrapositive theorem in opposite way, but it means that the previous one, it means that the given statement, but here we are just taking the wrong way. Okay, definitely wrong way means falsehood. Definitely my output also, I want the output also wrong, then only I can prove that the given statement is true. Okay, please remember this word H and not C. This is the main term in contradiction. Okay, contrapositive if not H not C, in contradiction if H not C. Okay, this is called contradiction proof. This is one of the method of to prove the statement or theorem. I have an example for that. Okay, let S be the finite subset of let S be the finite subset of some infinite set U. Okay, U is the whole set. This is infinite one. Okay, I'm taking another one set S. This is nothing but finite set. Okay, and T be the complement of S. Complement of S means the remaining part of U, right? U is the whole set, and from this set S is the subset. Okay, and I can say the T is the complement of S. That means that the remaining portion of U. Okay, some portion is defined in the S. Okay, then T is the complement, means the remaining portion of U. Okay, so T with the complement of S with respect to U, then T is infinite. Definitely it is true, right? U is the infinite one, and S and T are the subset of U. S is finite, already given, so the T should be in infinite manner. Okay, so how we can prove for this? Assume T is, we are going to prove with a contradiction. Okay, so I want to actually the S is finite one and U is a infinite. I want to do that, what T is a infinite one. I want to prove that T is infinite. Here I am taking in the contradiction manner. T is finite one. Okay, I'm taking that T is a finite one. This is opposite to our conclusion. Okay, so S is also, assume T is finite, S is also finite, then compute union of S union T. Okay, S union T will be also the finite one, because both the sets are finite, means S is having 4 elements and T is having 5 elements. If combine both the things, definitely we will get 9 elements. This is also finite one. I can count the numbers, so it is a finite one. Definitely S union T will be finite, but given that it is infinite, we are just here state that T is infinite. So hence our assumption T is a finite is a contradiction. This is wrong. Okay, this is wrong. I just assume that in opposite way. I just assume that in opposite way, assume T is a finite one, but I need to prove what T is a infinite. This is the thing I want to prove, but I'm taking in opposite way. T is the finite one. Okay, and S is also finite, already given. If you're competing both the things, combining both the things, S union T means it will be also the finite. Okay, S unit is nothing but what? The set, whole set, right? U set, the set U. This is not a finite. Already in the given statement, the givenness is, it is an infinite. But we are combining both the things, it will be in the finite. Okay, so it is wrong. So our assumption is wrong. The given is true. Okay, this is the contradiction. Another one theorem is A mod B equivalents to B mod A. If and only if A equal to B. This is same as the particular X is the real number, CL of X equal to floor of X if and only if X is an integer, right? Like that we are having, we know the mod operation, right? Modulo. What is the value? What is the value for this? 6 modulo operator 2. What is the value? Anyone?
0, ma'am.
0, ma'am.
Is it 0?
Yes, ma'am.
Yes, ma'am.
Are you sure?
Yes, ma'am. Reminder 0 only, no, ma'am.
Okay, then tell me what is
No.
the value? Correct only, ma. I just want to confuse you. Okay. What is the value for this?
2, ma'am.
How? How to?
2 divided by 6, remainder is 2. ma'am.
Okay, good. Others also know about this, right? This is the modulo operation. Okay. We just want to give the remainder value. If the particular the first argument or is a lesser one, we just do the same thing in the remainder. Okay, this is the output of the modulo operation. Okay, so now we move to the theorem. The 2 points, if a equal to b, then a mod b equal to b mod a. Assume a equal to b. Okay, want to prove that we can prove in two parts. That is, if you are assuming that A equal to B means, then we have to prove that A mod B equal to B mod A. Otherwise, if you are taking the A mod A mod B, right? Okay, no. Okay, we are taking that if A equal to B, then you have to prove that A mod B equal to B mod A. Please, you think when we will get this answer? A mod B equal to B mod A. When we will get? Try to substitute some values and try to find the answer. Then we will get the both. When we will get both the things are equal. When we will get this mark? A mod B equal to B mod A. When we will get both the things are equal, both the terms are equal.
If A equal to B.
Yes. If you substitute any other value, then you will find the answer. Okay. Otherwise, you have to muck up all those things. If you're substituting with some value, some integers, then you no need to muck up, you can write. Okay. When we will get A mod B equal to B mod A, in the case of A equal to B. Here, just as I'm assuming that A equal to B. Okay. A equal to B, I am assuming, so that I am given that A mod A. Okay. And B mod B, the same value. For example, the A and B is, I can say this is 6. So 6 mod 6 and 6 mod 6. What is the value? The remainder is 0. This is the module output of modulo operation, right? So remainder is 0. Then hypothesis, I can say A mod B equivalents to B mod A. Then what is the meaning that A equal to B? Okay. I just assume that A equal to B. For example, I'm taking the A and B value as 6. If you're substituting 6 mod 6 or 6 mod 6, then you get the answer is 0. Both are equal, right? When we will get, once we have the same value for A and B. Okay, so I can say A mod B and B mod A equal to equal means, what is the meaning? Both are equal. Okay, so I'm going to prove with the contradiction. Assume A is not equal to B. Okay, once we have the equal, once we have A equal to B, then only A mod B equal to B mod A. But here I'm taking the opposite way. A mod A not equal to B. Consider A not equal to B means, what is the meaning? That maybe A greater or B greater, right? This is addition for B greater. This is the A greater. Is it so? Both the things A and B are not equal. Then A may be the greater value or B may be the greater value. So I can represent like A less than B and A greater than B. Okay. So if A is less than B means, then A mod B equal to A. Is it so? A less than B, already I given with an example, right? 2 modulo 6. Okay, so 2 modulo 6 means what is the value? The output is 2. So it means that the A value is smaller and B value is greater. So here only mentioned the A value is smaller and B value greater. So A mod B is nothing but the value A, this 2. Okay, and this is the first equation. And next one, and B mod A. What's the value of B mod A here? This is A value, this is B value. B mod A is nothing but 6 modulo operator 2. What is the value? It is 0. I just explained with the example part. Don't confuse here and there. This is the example. And B mod A is nothing but, with the example, I can say this is the 0. Okay. This 0 is lesser than A. Okay. Is it so? I just taken with some number and try this. My value is, if A not equal to B. I have assumed that. So I want to substitute A and B in the with the equation means A is less than B means I will get the answer is A. And I'm doing doing another one operation, that is B mod A. That is also what? Less than A. Okay. This is A. This is less than A. Okay. So, but given 1 and 2 are equal. Okay. Hence, contradiction by symmetry, EB is less than A will have. Okay. So, from that we can conclude that this is what? This is less than 0. Sorry. This is equal to A. This is less than A. Okay. From this condition, I can say this is A less than A mod B is the A mod B is equal to A mod B is equal to A, and from here B mod A is less than A. Okay, A is the greater one. So I can say by symmetry B is the greater than, sorry, less than A. A is the smaller one. We'll have B mod A equal to B and A mod B equal to B. The same way I can say this one also. Okay, just changing the value. B mod A is equal to B and A mod B is less than B. Okay, the opposite way. Just I'm doing with the opposite way. Here I'm stating that with the A is lesser means we get the value as A. If B is lesser mean I get the value as B. So I can say A mod B is less than B. Here I can say A mod B is less than A. Okay, based on the A value, it's changing. By symmetry, I can say, I just proved the only one statement. By symmetry, I can say B less than A also. Okay. Hence, A and B is the scenario. No other chance, right? Both the things are equal. With the help of this condition, I can say, with the help of this example, I can say both the things are equal. Okay, this is the theorem for A mod B. If you are substituting with some other numbers, then definitely you will get the answer. No need to mark up all those things. You please try with some other value, 2, 6, or 3, 5. You're taking one value for A and one value for B. Then substitute with this. Definitely we will get the answer. Okay. What is the difference between contrapositive and contradiction? Both the methods are somewhat similar, but there is a primary difference. Okay, what is the difference? In contrapositive, we assume that not C and prove not H. That means given that H is if H then C, I am proving that if not H not C. Okay, this is the contrapositive. The method of contrapositive has the advantage that your goal is clear. That means we are taking all those things in opposite way. Just prove that. From that I can say the previous given statement also true. Okay, but in the case of contradiction, I'm somewhat confusing. That means no, our goal is to prove the contradiction. The opposite way only we have to prove. But it is not always clear what the contradiction is going to be at the start. At the start portion, we are not clear what is going. In the contradiction, what we are doing, just the opposite term for conclusion only, not for H. In the case of contrapositive, we are taking the opposite for H and C also. Both the things we are taking in the opposite way. Just want to prove that. Okay. From that I can conclude the given statement also true. But in the case of contradiction, we are not touching the H. I mean hypothesis. Just we are changing the conclusion value itself. So it leads to falsehood only, right? If you are saying with that is falsehood, definitely that is true. Otherwise, you are taking the assumption as we are taking in the opposite way. But we are not touching the H, changing the C only. That means the conclusion only. This is the falsehood statement. If I'm proved that particular thing is true, means what is that? If it is true means I can say the previous one is the false one. Okay, like that we can interchangeably we can say. Okay, this is the contrapositive and contradiction. You can remember any one of the theorem, that's enough. Okay, you please note what is contrapositive. and try with one example. You can say one example and one theorem. No need to go through all those things. Just you go with the only one example, which one is easy for you. Okay. And next one is the proof by counter example. This is not used technically. Okay, this is not technically used. Just we can say the example, you can understand what is my counter example. All multiples of 5 is even. Okay, all the statement given is all multiples of 5 is even. But in one case, 3 into 5 is nothing but 15. This is not a even. Okay, which is odd. The theorem is false. Wherever the theorem is going in wrong way, we just want to express the particular wrong way. We can, for example, we can take human. We can't able to react in proper way in all the situation, right? Based on the mood, it will change like that. In any one of the case, it may be fail. The fact or truth, it may be fail. Okay, and totally I can say I'm a good person, or one person is a good people or good heart they having, like that I can say. But I can't say with every situation, right? Totally I can say like that. We have some statements in universal, in truth. In universe we have some truth, all multiples of 5 is even, but in some cases it may leads to false of the particular theorem. Okay, so it is not used in practical. You please note what is meant by counter example. It merely way of showing that a given statement cannot possibly be correct by showing an instance that contradicts the universal statement. We are not using anywhere this one, but you please note the thing what is meant by that. Cannot possibly, which one is which case. For example, if I'm taking one program, 4 cases may test case may pass, one test case not passed, may failed, right? Like that. If you are focusing on the failed one and taking to define the particular false one, this is the counter example. Okay. I can say 90% it is good only. In some cases, some test cases, it may not working. So this is the counter example. The next proof is the inductive proof. Inductive proof is nothing but a recursive kind of proof. In that we have 3 types. Okay. Induction on integer, induction on structure, and mutual induction. Okay, this is nothing but it is we have one problem in this mathematical induction. Okay, it is very important. We just need to focus on 2 points here. One is basics and another one is induction. Okay, basics is nothing but initial value where we can start the particular theorem. Okay, initial value or least value to state the particular theorem. Okay, the induction is nothing but it is a additional step. For example, in the case of basis, we have to take with n equal to 0 or n equal to 1. Okay, and induction means n equal to k. For some other value, we have to take most value or maximum value, n equal to k. And another one things, in induction, we have 2 steps, n equal to k plus 1. Just want to substitute all those things in the particular form or particular theorem. Okay, we can mainly in these 3, the induction is first one, induction on integer. The mathematical induction is very important question. They may give like this, given one problem and want to prove this both the things are equal. Okay, how we can do means with the help of basics means I have to tell with n equal to 1 because the initial value is 1. So I have to go with n equal to 1, substituting both the left hand side and right hand side with the value 1. We have to check whether both the things are equal. If it is equal, then I can say it is a proved one. Okay, not I can't say with the initial statement. I have to go with the next step, that is n equal to k. Each and every problem, the same thing we are going to follow. First of all, we are going to substitute n equal to 1, and we have to prove left and right are equal. And next one is the n equal to k. We are going to substitute, and for that we have some equation, not an exact value, we have some equation, we will get some equation. And the third statement you have to do with n equal to k plus 1. Okay, we have to substitute n equal to k plus 1, and with both the things, with the help of this we can try to solve and try to find the left hand side equal to right hand side. Okay, all the problems following the same procedure only. Okay, basis condition we are going to supposed to substitute n equal to 1 or 0. Okay, here the initial value start with the 1 only, so I just start with the 1, no need to go with 0. And next one is n equal to k and n equal to k plus 1. These are the three main thing we are going to do. For the n value we are going to substitute in this equation and try to find what is the value for n equal to 0, n equal to 1, n equal to k, n equal to k plus 1. Okay, just want to prove the left hand side equal to right hand side. Okay, we will see in the next class. Tomorrow we have first star class. In that we will see what is by inductive proof, and the main is the mathematical induction. Okay, thank you students, we will meet in the next class. You can leave.